Hello everyone. In this session I'm going to teach you the basics of complex numbers. More precisely, I'm going to teach you the definition of complex numbers, and I'm going to teach you how to add and multiply complex numbers. That is all. We'll not do any advanced things such as complex number division, just multiplication and addition. First, the definition of complex numbers. The set of complex numbers is denoted with this fancy letter C. So all complex numbers are denoted with this special letter C, which is written with this kind of a double line on the side. So what are complex numbers? The complex numbers C are all numbers of the form a plus b times I, where a and b are real numbers, and the number I is a number called the imaginary unit with some special properties, of which I'll tell you in a second. So if I were to write an arbitrary complex number, well, I would have to write something like, let's say, 2 plus 3 times I would be an arbitrary complex number, right? So constant plus another constant times I. The numbers 2 and 3 are real. The numbers a and b are real. And I is some special number which I haven't defined yet. Okay, now let's focus our attention on the special number I. That special number I is called the imaginary unit. So that special number I is called the imaginary unit, and it has a very special property. I squared is equal to -1. So that number I has a very special algebra. Its square equals -1. Okay, now let us focus our attention on the equality I squared equal to -1. Let us apply the radical operation on both sides of that equality. Now you may wonder what is the definition of radical of -1. Perhaps you may have heard before that we're not allowed to take radical of negative numbers. Maybe you've heard that, maybe you haven't. So I'm taking this operation completely formally. I'm imagining what would happen to this equality if I were to apply the radical operation on both sides. So let's not be bothered with whether this operation is defined or whether it makes sense. Let's just formally apply it and use the properties of algebra that we know from high school. Okay, so radical of -1 equals radical of I squared, but radical of something squared, let me remind you that radical of something squared is plus or minus that thing. So plus or minus I is equal to radical of -1. Now, the fact that plus or minus I is equal to radical of -1 is a consequence of our desire to have that I squared be equal to -1. Once again, we define the number I as some number whose square is -1, and that automatically forces I to be plus or minus I to be equal to the radical of -1. So our definition of the number I implies that either plus or minus radical of -1 must be I. Now I is a single number, not two numbers or a collection of numbers. So we cannot have that I is plus or minus radical of -1. We have to choose one of the two, either plus or minus. Now, by the definition of the radical function, radical of -1 is exactly equal to I. So of the two possible choices for radical of -1, we are choosing radical of -1 to be equal to I rather than -I. Alright, so that covers the basic algebra, the basic definition of complex numbers. Now I have to teach you how to compute with complex numbers. Now here are the rules for complex addition, and here are the rules for complex multiplication. Now these rules look rather complicated, and I could of course read the rules right now for you, but rather I want to teach you how to do complex addition, and I want to teach you how to do complex multiplication on concrete examples. So once again, the rules for complex addition and multiplication are spelled out here. Feel free to read them, but I will just directly teach you how to do complex addition, subtraction and multiplication on examples rather than read these rules for you. Okay, now let's start with an example with just two simple numbers. Let's start with the number u equal to 2 plus 3 times I. Let's have the number v be equal to 5 minus 7 times I. Just a reminder, I was that special number for which I squared is equal to -1. So let's start with these two numbers u and v, and let's do the three easy algebraic operations with them. Let's do their sum, let's compute their difference, and let's compute their product. Alright. Now let's start with the sum of the two numbers. Now, since u is 2 plus 3i and v is 5 minus 7i, we can replace u with 2 plus 3i and v with 5 minus 7i. Now, yeah, as you can see, the notation for complex numbers more or less follows the notational conventions for arbitrary numbers. Alright. Now, I skipped the rules for addition of complex numbers, so now let me tell you how complex number addition is actually done. What you want to do is you want to pretend that this expression here is a polynomial or just an arbitrary algebraic expression where I is some variable. You want to do the same with that expression, 5 minus 7i, and you want to group terms as if these two objects were polynomials. So you want to add 2 plus 3i and 5 minus 7i as if those were regular algebraic expressions, treating I as a variable. So in particular, you'd have to add 2 and 5. So when you add 2 and 5, you get 7. And then you'd have to add 3i with negative 7i. So when you add 3i with negative 7i, you're going to get, well, 3 minus 7 is negative 4, so you're going to get negative 4i. And indeed, when you do that, let's see, you have to group this term with this term, so here 2 and 5. You have to group this term here with that term, and you notice that you have a common factor of I in both of these terms, so you can factor out I just as I did here, right? So from these two terms you can factor out I, okay? And when you factor out I, you're left with 3 minus 7. Now 3 minus 7 is negative 4, so altogether you get 2 plus 5, 7. So altogether we get 2 plus 5 equal to 7, and 3 minus 7 equal to negative 4. So 7 minus 4i. Once again, complex addition works the same way as a polynomial addition or any other addition that we have seen so far. Now, subtraction of complex numbers works in a very similar fashion. So if I want to subtract v from u, v was 5 minus 7i, u was 2 plus 3i. So what I'm going to have is, when I subtract these two numbers, 2 minus 5 is going to be equal to negative 3. 3i minus minus 7i is going to be equal to 3 minus minus 7, so 10. So 10 times I. So altogether I'm going to be getting 7 plus 10 times I. Indeed, when I subtract these two numbers, 2 minus 5 is here, and 3 minus minus 7 is here. 3 minus minus 7. So this minus here and that minus 7 here is here. So 2 plus 3i minus 5 minus 7i is 2 minus 5 plus 3 minus 7 times I. So we get 2 minus 5 is negative 3, and 3 minus 7 is 10. So 3 minus 7, 10. So times I. So minus 3 plus 10i. All right. Finally, let's do complex multiplication. Now, complex multiplication is a tiny bit more involved than complex addition and subtraction. Now, just as with complex addition and with complex subtraction, when we do complex multiplication, we uncover parentheses and we do operations as if we're dealing with regular algebraic expressions. So we imagine that 2 plus 3i is a polynomial with respect to the variable I. We imagine that 5 minus 7i is another polynomial, and we uncover the parentheses. We FOIL just in the usual way that would be done with usual polynomial expressions. All right. So now let's uncover the parentheses. Now, when I multiply 2 times 5, I get, well, I guess I get 2 times 5. Next, so I first multiply the first terms. Now I'm going to multiply the outer terms. So 2 times negative 7i, so 2 times negative 7i is there. Next, I'm having 3i times 5, that goes next. And finally, the last terms is 3 times I times negative 7i. Please do not forget to put the parentheses around negative multiplication, so do not forget the parentheses here and do not forget the parentheses there. Okay, so we've put all of our parentheses. Now let's carry out the operations. 2 times 5 is equal to 10. 2 times negative 7 is equal to negative 14, and we have an extra I, so that an extra I which is copied here. Okay. Next, we have 3i plus 5. Well, 3 times 5 is 15, so 3i times 5 is 15i. Next, we have 3i times negative 7i. 3 times 7 is 21, so together with the negative sign we get negative 21i squared. So what happened so far? We started with the two complex numbers u and v. This was u, this was v, and we multiplied them out as if they were regular algebraic expressions, and we got 10 minus 14i plus 15i minus 21i squared. Now, so far, the operation that we did was very much similar to usual polynomial manipulation. So we have so far never used the fact that I squared is equal to negative 1. So the fact that I squared equals negative 1, I haven't used it anywhere so far. Alright, let's continue our computations. Minus 14i plus 15i, well, I could factor I, and then I'm getting 15 minus 14. 15 minus 14 is 1. So here I'm getting 1 times I, and the convention is that when you have 1 times I, you can abbreviate that as the number I. So you don't need to spell out the number 1. So the coefficient 1 you can omit it. Okay. Now here's the really deep thing. As we said, I squared is equal to negative 1, and we haven't really exploited that fact so far. Well, let's exploit it. I squared equals negative 1, so I can replace 21i squared with minus 1 times 21. So rather than 21i squared, I'm getting negative 21. Alright, I'm almost done. Now I'm having the expression 10 plus I minus minus 21. Now minus minus 21 is equal to plus 21. So I'm getting 10 plus 21 plus I. And now 10 plus 21 is equal to 31. So once again, 10 minus 21 is equal to 31. So finally I get 31 plus I. That's it. I carried out my complex number multiplication. By the way, I started with a number of the form a real number plus a real number times I. I had another number of that form, a real number plus another real number, negative 7. So the real number 5 plus the real number negative 7 times I. So I had two complex numbers. I multiplied them out. And when I multiplied them out, well, following common sense, I would get this expression, which depends on also on I squared. So that expression would not be of the form a real number plus a real number times I, but I exploited the fact that I squared can be replaced with negative 1 in order to convince you that the product of two numbers, two complex numbers, so two numbers of the form real number plus a real number times I. So a product of two such numbers is again, after some simplifications, transformed to the form a real number plus another real number, the number 1 times I. Alright, so hopefully I've convinced you that the product of two complex numbers is indeed a complex number. Not only did I hopefully convince you of that, but I hopefully taught you how to actually do this operation. Alright, now I want to finish this short exposition of complex numbers by quickly overviewing the basic types of numbers that I expect you to have seen so far. First, we have the integers or whole numbers. The integers are simply the numbers 0, 1, 2, 3, 4, all the way to infinity, and also integers include the negative numbers, negative 1, negative 2, negative 3, and so on. I'm sure you have seen integers before, and you know how to compute with them. Okay, now we have also seen so far rational numbers. Rational numbers would be just quotient of two integers. A typical rational number would be the number 1/2 or the number 2 over negative 3. Now, when I say quotient of two integers, well, we know that 2 divided by negative 3 is the same as negative 2 divided by 3. So 2 divided by negative 3 has got to be identified with negative 2/3. So when I say that a rational number is the quotient of two integers, I mean, sure, a quotient of two integers, but we remember in our heads that two different pairs of integers may yield the same quotient. For example, the number 2 divided by the number negative 3 yields the same quotient as the number negative 2 divided by the number 3. Of course, now you're going to say, well, this is just a matter of sign, but there's a more serious example of that. If I take the number 8 and I divide it by the number 12, well, we remember that there's a common factor of 2, so you can cancel top and bottom a common factor of 2, because 8 is equal to 2 times 4, and 12 is equal to 2 times 6, and you can cancel out the 2. So 8 12s equals 4 6, and then again 4 6 equals 2 times 2 over 2 times 3, and you can cancel out another factor of 2. And you get that 8 12s is the same as 4 6, which is the same as 2/3. So the pair of numbers 8 and 12, when you take their quotient, you get the same quotient as when you take the pair of numbers 4 and 6, and you get the same quotient as when you take the numbers 2 and 3. So we remember that quotient of two integers are not unique. We remember that rational numbers have non-unique representations. Okay, two different ways to get a pair of number whose quotient is a given rational number. Okay, next we have also studied the real numbers. Now, what real numbers do is they measure the location of a point on a real line. For example, here's the number radical of 2. The number radical of 2 is approximately equal to 1.4142 and so on all the way to infinity. But the number radical of 2 has an infinite decimal expansion. So such real numbers measure distances from the real line. And real numbers are allowed to we usually represent them with decimal notation when we want to get approximation for real numbers. Real numbers are allowed to have infinite decimal notation expansion. Here a few famous numbers. The number pi is a very famous real number. The number e is a very famous number. The number -1 is a famous number as well. So rational numbers represent quotient of integers, and real numbers represent distances. Of course, rational numbers also represent distances. For example, here's the number -1/2, right? So that would be a rational number. But real numbers are finer, so they can give you a better approximation for distances than rational numbers. Now the exact details on how to construct a real number which is not rational, that's a little bit tricky, and I will not do that here. But I just want to tell you that the numbers that you see here, radical of 2, e, and pi, those three numbers cannot be represented as the quotient of two integers. One can demonstrate that. I'm not doing that here, but it is possible to prove that. Okay, now finally we have a fourth type of numbers that we have studied so far. This is the type of complex numbers, the numbers we just studied. Things like 2 plus 3i, that would be a typical complex number. Or the number -i. By the way, the number -i, that's just the number 0 minus I, right? So the real number 0 minus the number I. We can omit the 0. We don't need to spell out the 0 in our notation for complex numbers. Alright, now one short note, all integers are rational numbers, all rational numbers are real numbers, and all real numbers are complex numbers. So the set of integers is a subset of the set of rational numbers. The set of rational numbers is a subset of real numbers. That means that every rational number is a real number, but there are real numbers that are not rational. And the set of real numbers is a subset of the set of complex numbers. So every real number is a complex number, but there are complex numbers that are not real numbers. Alright. Now, I gave you a neat geometric interpretation of the real numbers. Those measure distances on the real line. And of course, since every integer is a rational number and every rational number is a real number, that real line gives you also a good interpretation of integers and rational numbers. But an interpretation of the complex numbers that can be given, so one can give such an interpretation, but it just goes beyond the scope of this very, very short introduction to complex numbers that we just did here.